Hi class. In this video we'll continue to talk about energy, and we'll talk more specifically about kinetic energy in the context of collisions. So as an example case, let's consider a collision. So I'm going to draw two blocks here to represent two objects speeding at each other. So object 1 has mass 1 with velocity 1 this way, and object 2 has mass 2, velocity 2 this way. All right. And now what happens here is that we know what these values are. So mass 1 is 1,300 kilograms. Mass 2 is 2,600 kilograms. We also know that the speed v1 is 30 meters per second, and speed 2 is 15 meters per second. All right. Good. So now what happens here is that they will eventually collide. So then object 1 is right here now. Mass 1, and object 2 right there. M2. And they stick together. So let's say they bend each other out, and so now they're just stuck together. And what I want to know is I want to know at what velocity they will move together. Good. So this is just, you can see this as a small quick review. Now, you know by now that there's a collision here, and the most effective way to solve this collision is using conservation of momentum. So meaning that the total sum of all the initial momentums, it needs to be the sum of all the total final momentums. Now, if you like to use this as an example, I would now stop the video and try to figure this out. See if you can figure this out, this velocity final here. All right. Okay, so you hopefully took a shot at it. So let me quickly go through it. There is a momentum 1 to the right, momentum 1 to the left. This means that I have mass 1, velocity, speed 1, minus mass 2, velocity 2. Again, this is the sum of both momentums, and I already accounted for the fact that I called this direction the plus direction. Okay, and then this needs to be equal to, now these are together, you can sum them up, mass 1 plus mass 2, velocity final. A little bit of algebra will get you to what this looks like in terms of the number, in terms of the equation you need to solve to figure out the speed. And this is mass 1, velocity 1, minus mass 2, velocity 2, divided by mass 1 plus mass 2. All right. So now we go ahead and just solve for this. This is 1,300. Excuse me. This is 1,300 kilograms, and then multiplied by 30 meters per second, minus 2,600 kilograms multiplied by, and might have to do this. Okay, multiply by 15 meters per second. Now you divide by the sum of the masses. So it would be 6, 7, 8, 9, 3,900 kilograms. Now let's check our units. Kilograms go away. So the only thing left is meters per second. Great. So go ahead and punch this in the calculator, and you will probably find that in this case, velocity final equals to 0 meters per second. Which means that both of these objects were traveling towards each other, and they stuck together and they're not moving. So finally this speed right here is 0 meters per second. They're stuck. And if this seems familiar, that's good, because this was our first video, and this is more or less very similar to what we did with that. Okay, so this only happens in a very specific case, very special case. So if you take mass 1 and velocity 1 and you multiply these two together, you will find the magnitude of P1 initial. If you take these two numbers here and you multiply together, you get them P2 initial. And since they're pointing to each other, you will find that these two numbers multiplied together are equal to these two numbers. So what happened is this is equal to this. So whenever this happens, both objects stop. Very rarely this is the case, but this is the case for the first example and for this example. Okay, so let's say we talked about kinetic energy, right? We solved this problem using conservation of momentum. But some of you may have remembered that in our last video we introduced the idea of kinetic energy, that is energy that is inherent to motion. So this object here is moving. If this object is moving, that means that there is a kinetic energy due to object 1 at its initial position. And object 2 is also moving, therefore there needs to be a kinetic energy associated to this object, and since this is initial. What do you think there will be? So we already, if you multiply these two numbers together, they will be the same. Momentum, the momentum due to object 1 is the same as the momentum due to object 2. And these objects, they stopped. So will the kinetic energy initial for the first object be the same as the kinetic energy initial for the second object? That is, what I'm asking you is kinetic energy also conserved in this collision? Well, we know what kinetic energy looks like. So we can actually go ahead and carry out the calculation. So let's go ahead and do it. So kinetic energy of object 1 initial is 1/2 mass 1 velocity of object 1 initial squared. I'm sorry, speed. Again, this does not account. So this is a number. There's no vector quantity. This is also a number. There's no vector quantity. Also, it does not matter if you put a negative number here. You're going to square it. The only possible number you're going to get from a square is a positive number. So let's go ahead and calculate this. This is 1/2 1,300 kilograms multiplied by 30 meters per second, whole quantity squared. If you carry this calculation out, you'll find that it's 585,000 joules. So this is the amount of energy that object 1 brings in due to motion. So let's find out what object 2, how much energy object 2 is carrying out in this. So the kinetic energy of object 2 initial is 1/2 mass 2 velocity 2 initial squared. And these numbers are 1/2 2,600 kilograms multiplied by 15 meters per second squared. And if you carry out this number, you will find that it comes out to 292,500 joules. Which means that this amount of energy here is vastly different than this amount of energy. Which means that object 1 had more energy due to motion, even though it's lighter. You see, this is 1,300 kilograms. This is 2,600 kilograms. So matter of fact, object 2 is twice as heavy as object 1. And object 1, but object 1 is going twice as fast as object number 2. And kinetic energy is dependent on the square of the velocity. So what happens with kinetic energy of the final object? So if we treat M1 and M2 together, what do you think the kinetic energy for objects 1 and 2 combined will be? Well, hopefully you can see that the combined kinetic energy will be 0 because the speed is 0, right? So just for completeness, if we take the kinetic energy final is 1/2 mass 1 plus mass 2 times the velocity or speed's final squared. This speed here is 0. So whatever you multiply this over is going to be 0. So this is 0 joules. Which means that there's a very powerful conclusion for this. It's that the total sum of all of the kinetic energy initials does not equal the sum of kinetic energy final total. And comes a disclaimer here for most collisions. So for most collisions, this right here, kinetic energy is not conserved. So in this class, every time I give you a collision, kinetic energy should never be the thing you go for, because you cannot guarantee that kinetic energy is conserved. However, for every collision, this goes with anything within this class or anything within every collision ever, momentum is always, always, always conserved. There is a very special case in which kinetic energy is conserved. And that special case is special case. So right here, if the collision is elastic, then you may say that the total sum of all of the kinetic energies is the sum total of the final kinetic energies. All right. Now, what is the ratio that this happens? And the ratio that this happens in real life is that almost no collision is elastic. So in real life applications like car collide with car collide with object, um, two objects collide, the majority, um, the majority of collisions will be not elastic. So this will be the majority of them. So in real life, this is the majority of cases. Meaning that elastic collisions are very special. They're very rare. So in this class, well, whenever you see an assignment or test question and it is a collision and it is not stated explicitly that the word elastic does not show, if the word elastic does not show, then you cannot assume that kinetic energy initial and final are the same. However, if the word elastic shows up, then kinetic energy is conserved and it is appropriate to use it. All right. So that concludes the idea of kinetic energy in collisions. Now I want to ask you, this just intuitively, does this make sense? I'm sure that most of you by now have heard the term energy cannot be destroyed or created. So we started this class by saying momentum cannot. So whenever you write a conservation of momentum like this, right here, that is a statement that says that momentum cannot be created or destroyed. And so in a collision like this, so momentum is always conserved. And some of you may have heard the idea that, oh, energy cannot be created or destroyed. However, I just gave you a one example here of this collision in which all of the energy is gone. So you had, when you sum this all up, it's about 7, and so it's about a million, there's roughly a million joules worth of energy that goes into this collision, and it's all gone. How do we reconcile the fact that we lost a million joules worth of kinetic energy to nothing and say that energy cannot be created or destroyed? I want you to listen very closely. I have a pen in my hand and I'm going to drop it. I'm sure you could hear it. For those of you who know or don't know, sound waves are waves that carry energy from one point to another through a medium. Matter of fact, you could have, there's something called Mach number in galactic astronomy. It's the sound, it's how fast sound goes through the intergalactic medium. So whenever you have, and sound waves can also propagate in water. So the speed at which they propagate is dependent on the medium. However, every sound wave, regardless of the medium, does the job of carrying energy from one place to another. So that is where this 1 million joules went to. Part of it went to sound. Part of it went to thermal energy to heat up some of the materials. The fact is that if the collision is elastic, it means that 100% of all the energy is retained in motion. But if the collision is not elastic, and for most collisions they are not elastic, that means that energy was converted from motion to other types, which means this. So let's come up with a couple of examples of kinds of energy we're going to see in this class. So kinetic energy is the energy due to motion. And then soon we're going to see something called gravitational potential energy. which is it's the energy. Well, this is a tricky one. It's energy due to raising objects against gravity. So energy due to gravity. Let's just simplify this to gravity. Okay. Now, in this case, we've lost energy to some of the things we cannot track with an equation in this class. But these two will be things that we will be able to track in this class. And what I wanted to point out is that energy cannot be created or destroyed. And we sum that, we can say that that is due to the fact that energy is conserved, which means that the total energy initial needs to be equal to energy final. But for this to work, you have to include all sources of energy. All sources of energy. Sources is a bad word, I'm sorry. All types of energy. So let me go and fix that real quick. So if somehow you could go back and count. So in this case, so let's go back to our collision real quick. If you could count all the energy terms out of here. So let's say you have comes out here the energy due to sound, and if you could keep track of the energy lost to thermal interaction, then you will find that the energy lost to sound, the energy lost to thermal interactions, and all the other energies will be equal to precisely 1,000,000 joules, which is the amount of energy that we lost to motion. Because things were in motion, and then all of a sudden they were no longer in motion. This is the first time you have encountered conservation of energy. We will expand this idea on this upcoming week.